Okay, I'm going to try a magic trick. So I've got a rabbit in a hat. I'm going to put the rabbit in the hat. Okay, put the rabbit in the hat. And presto, changeo, I don't know what the right magic words are, it's disappeared. Ta-da. Okay. All right. Great trick. So what I want to do is a problem with magnetic fields. So let's say that we've got two current carrying wires, and let's say that they carry currents I1 and I2, and they're separated by D. So they're parallel current carrying wires. Same kind of problem we've seen, same kind of setup we've seen before. But I want to ask a different question, not about force, but where is the magnetic field equal to 0? Where is the magnetic field equal to 0? So the answers are A, everywhere. Okay, here are your answers: everywhere, nowhere, halfway between, somewhere. But it depends on I1, I2. So I'll give you a second, or you should pause it and think about it and try to answer it for yourself. But 3, 2, 1, the answer is somewhere. Okay, there is a 0 somewhere, and we just got to figure out where. It might be halfway between, depending on the relative currents, but not necessarily. So how are we going to do this? Well, first of all, I want you to think conceptually what's going on here. I1 creates a magnetic field which circulates around by the right-hand rule. Put your thumb in the direction I1, and so it goes around where it's coming out of the page over here, and it's going into the page over here. And that's true all the way along I1. I2, same thing. Point your thumb in the direction, your fingers go around so that it's coming out of the page here and into the page here. Okay. So the first thing that you can see is between I1 and I2, the field due to I1 points into the page, and the field due to I2 points out of the page. This is the field due to I1, and this is the field due to I2. The thing that I didn't do is to ask, okay, so now we know between them that those two fields point in opposite directions. But what about out here? What about out here? I2 has a field that points into the page, but what about I1? Well, now we've got to just go to a larger radius. I1, right? Here's a field vector for I1. The direction. Sorry, I don't know what I did. Between the two, the magnetic fields go in the opposite direction. So that's the only place that they can cancel. So B2 comes out of the page, and B1 goes into the page everywhere between the two, and it just depends on the relative magnitudes. So what we need to do is we need to choose some arbitrary distance from one and the other. Remember, the whole distance is D. So let's just say at some distance r from I2, the magnetic field due to I2 has a magnitude of B2 equals mu naught I2 over 2 pi little r. Okay, so that's the magnetic field due to current 2. And that points out of the page. What is the magnetic field at that same point? What is the magnetic field at that same point due to current 1? Well, it's mu naught I1 over 2 pi. It's not r, right? Because what's the distance from I1 to that point? This distance here, what's that distance? We can call it r1 if we want, but actually we don't need another variable because it's just d minus r. So at that same point, the magnetic field is due to 1 is mu naught I1 over 2 pi d minus r, and it's into the page. We already argued why it's into the page. So in order for the two to cancel, one's out and one's in, then they just have to be equal in magnitude. Or we can write it either way, right? We can write it as a vector equation, we can write it as a scalar equation. We can say they're equal in magnitude, or we can say, we can sum them as vectors, right? B1 plus B2 is equal to, if we choose out as the positive direction, that means in is the minus direction, then B1 is plus mu naught I, whoops. Sorry, let me start again. Sorry, I said out is positive. I meant to say in is positive. Doesn't matter. We'll keep out as positive since I chose that. In is negative. Then since B1 is in, it's going to be negative. B1 is mu 0, has a magnitude mu 0 I1 over 2 pi d minus r. This is a positive number. That's the magnitude. But the negative out front tells you it's in the negative direction. B2 is in the positive direction because I defined out as the positive direction. Plus mu 0 I2 over 2 pi r. The net field is 0, right? We're asking where is B equal 0. Okay, so we need to solve this equation to find where B equals 0. What do we mean solve that equation? What is the unknown? D is given, I1 is given, I2 is given. What we want to know is what is R. So I need to solve for R in this equation. Okay, so I added the negative thing to both sides. I cross-multiplied. I canceled the constants. And so I did 3 steps of algebra. And in those 3 steps of algebra, whoops, I got to change something. Hold on. In those 3 steps of algebra, I got this equation. And so therefore, whoops, and I still messed up. I got this equation. And so therefore I get that the distance from I2, the distance from I2 is I2 over the sum of the two currents times D. Let's just make sure that makes sense. Let's say, for example, we know that if, or you probably could see that, for example, if I2 equals I1, then we would think that if they're equal and the field cancels somewhere in between, then it probably cancels in the center. And if I2 equals I1, therefore R equals I2 over I2 plus I2 times D, which equals 1/2 D. Okay, that makes sense. Let's go ahead and think if I1 is smaller than I2, right? If I1 is, let's make I1 bigger than I2. If I1 is bigger than I2, let's make example I1 equals 2 amps and I2 equal 1 amp. Therefore, R is equal to 1 over 3 or 1/3 of D. So if I2 is bigger, in order for them to cancel, I keep saying the wrong way around. If I1 is bigger, in order for them to cancel, I got to be farther from I1 and closer to I2 in order for them to cancel. And saying R is 1/3 of D, that's closer to I2 than it is to I1. So that makes sense. So this is the position at which the two fields cancel. In between, R is the distance from I2 in between the two currents.